This is video 1 of topic 2 of the course, which is on the atmosphere and weather systems. More information on this topic is available in your textbook on pages 8 through 23. In this video, we cover atmospheric parameters, and subsequent videos in this topic will cover clouds, general circulation, air masses and fronts, and extreme weather and an introduction to precipitation. In a synchronous class section, we're going to talk about atmospheric parameters and do some examples. Of course, weather is critical for hydrology. Atmospheric weather systems are fueled by solar input and characterized by air masses in motion, circulating winds, cloud generation, and changes in temperature and pressure. These are the things we'll cover in this section. And why is this important? Well, of course, the atmosphere is the major hydrological link between oceans and the continents. But probably more importantly, the hydrological cycle is shaped by atmospheric conditions with precipitation as the major input to the hydrological cycle on the Earth's surface. And water vapor content of the atmosphere is a major component of the atmospheric processes that create weather in the lower atmosphere. In this video then, we'll talk primarily about pressure, density and temperature, humidity and vapor pressure, and latent heat. You're already familiar with the topic of pressure. It's simply a force per unit area that's exerted on a surface, and it's measured in newtons per square meter or pascals. Atmospheric pressure measures the weight of air per unit area, and so at sea level, the average air pressure is about 1 atmosphere. 1 atmosphere, measured in units of pressure, is 101.3 kilopascals, or in millibars, 1013 millibars, or in millimeters of mercury, 760. Atmospheric pressure decreases with altitude because the density of air molecules at elevation decreases. And then, of course, it's important to recognize that horizontal and vertical pressure changes in the atmosphere produce wind, and it's wind that drives most of our weather. You should be familiar with this equation from previous classes. The ideal gas law is P is equal to rho RT. P is pressure, rho is density, R is the gas constant, and T is the absolute temperature. And so the ideal gas law relates pressure, density, and temperature. Important implications of this equation are that at constant density, P is directly proportional to temperature, and so an increase in temperature will cause an increase in pressure. Also, pressure is directly proportional to density, so for fixed pressure, a decrease in temperature causes an increase in density. And so, interestingly, cold air masses are usually associated with a higher pressure than warm air masses. You've probably seen this sort of chart before. It shows pressure and weather fronts, and pressures are expressed here in millibars, where 1 millibar is 100 pascals. And you can see all of these different numbers here that indicate different pressure. And you can see a high pressure system here and a low pressure system here. We'll talk more about these in subsequent videos in this section. Humidity is another very important atmospheric parameter. We know that there's a mixture of gases in the atmosphere, and it includes water vapor. Humidity is a measure of the amount of water vapor in a fixed parcel of air. You also probably remembered that the air is primarily nitrogen, so about 78% nitrogen, about 21% oxygen, almost 1% argon, and then between 0 and 4% water, depending on the level of saturation. There's also carbon dioxide and other trace gases. So then relative humidity is a ratio of the air's actual water content to the amount at saturation for a given air temperature. So here are a few simple examples. Let's imagine that we have a flask here of air containing also some water. Okay, and so to begin with, we know that at 25 degrees Celsius, the air can contain as much as 20 grams of water vapor. Currently we have 5 grams, and so that means we're at 25% of the limit. And then as the amount of water vapor in the air increases towards saturation, we can get as much as 20 grams. And so when we have reached 20 grams in this air here, we have a relative humidity of 100%. You should also be familiar with the concept of partial pressure. So a partial pressure is the pressure on a surface of a container from a particular gas in a mixture. And so if we think about air, for example, we know that gas A may be nitrogen, gas B is oxygen, and let's imagine that gas C is water vapor. Then we can figure out the total amount of pressure in that container by adding the pressures created by each of these different gases. Vapor pressure is the partial pressure that's exerted by water vapor. Saturation vapor pressure is the pressure of water vapor at its maximum capacity in the atmosphere. Now, if you're interested, you can actually try an interesting example at home that shows you the effect of saturation vapor pressure. Okay, so the YouTube link is here if you'd like to try that. Now, interestingly, vapor pressure is dependent on temperature. So as temperature rises, the amount of vapor that can be held in the air also rises. And we can see this in the world around us. So as air lifts and cools as it moves upwards in the atmosphere, the relative humidity increases to the saturation point. And we can see where the air is saturated because we see clouds. Okay, so vapor then begins to condense into liquid water, which forms clouds. You can also see this on the Earth's surface, on grass, for example, in the summertime. So the dew point temperature is the temperature to which a sample of air that contains a certain amount of water must be cooled to reach the saturation point. Okay, so you see these little droplets of water on the grass because the air temperature is cooled to the point where vapor will begin to condense into liquid water. You can also try at home another example from YouTube that shows you how dew forms. There's an important equation for the vapor pressure. Vapor pressure is given as the symbol E, and it's rho RT over 0.622. E here is the vapor pressure. It's measured in millibars, which again is like pascals or kilopascals. Rho W is the vapor density, or the absolute humidity. It's measured in small units of grams per cubic centimeter. R is the dry air constant, which has these strange units, 2.87 times 10 to the 3 millibars, centimeter cubed per gram Kelvin. T is the absolute temperature in Kelvin, and 0.622 is from the ratio of the molecular weights of water to air. And the value you'll get here is typically between 1 and 2% of the total atmospheric pressure near the Earth's surface. At saturation vapor pressure, E is written with a subscript, so E becomes E sub S, and it can be found from this empirical equation. Okay, so all you have to do here is plug into this longer equation the temperature now in Celsius. And that will give you the saturation vapor pressure for air at a certain temperature. This is, again, an empirical equation, so it's data-based, and it's used to find the saturation vapor pressure over water, and it's accurate to about 0.5% for a certain range of temperatures between 0 degrees Celsius and 40 degrees Celsius. Relative humidity is the ratio of the current water vapor pressure to the saturated water vapor pressure at a certain temperature. And so as an example, your relative humidity is going to be 100 times the actual vapor pressure over the saturation vapor pressure. So here are some sample typical relative humidities for different cities in North America. Houston is a relatively humid location. So its high level of humidity would be 89% of saturation, and its low would be about 67. Chicago is somewhat drier, it's 80 and 64. New York is a little bit lower again, 72 and 56. And then as we get into the mountains or more arid regions, the values go down. And so Denver is about 67% and down to 40%, and Las Vegas, as you would expect, has quite dry air, low relative humidity, and so its high is about 40 and its low is as low as 21. And so you would feel that in your skin. It would actually begin to really dry out your skin. If you're interested in how to measure the relative humidity with a fairly commonly used instrument, you can look up a psychrometer, and it uses what are called dry bulb and wet bulb temperatures. Okay, you may have heard of those as well from meteorologists, for example. So you can look that up here at this YouTube address. And this is what a humid day looks like. This is what a very dry day looks like. Another important equation for humidity is the specific humidity. This is the mass of water vapor in a unit mass of moist air. So how many grams of water vapor for every gram of the mixture of air? It's equal to the ratio of densities of the vapor density and the density of moist air. And we can find it by solving this equation. Okay, when you solve here, you end up with this. So the density of the moist air is equal to the pressure over the gas constant times the temperature, times 1 minus, and then these components here. And if you think carefully about what this means, it's actually quite interesting. What it shows you is, remember, this is the vapor pressure, this is dry air. So what it shows you is that moist air, because of the minus sign, is actually lighter than dry air. And if you think about that, that makes sense, because the molecular weight of air is higher than the molecular weight of water, right? 29 versus 18. We can rearrange that previous equation a little bit, and then we can write an equation for what's called the specific humidity. It's the ratio of the vapor density over the moist air density. So these are some equations that you might have to use if you're trying to determine values for atmospheric parameters. Now, in the atmosphere, there can be many changes of state as well, of course. So water can change state between solid, liquid, and gas under normal atmospheric conditions. So think about the cloud itself, or the air around the cloud, which contains water vapor. Within the cloud, you can have either liquid droplets, or you can have solid droplets, so little ice pellets or little ice crystals within the cloud. These phase changes that occur absorb or release energy. And so you can have melting and freezing, and you can have evaporating or condensing. For vapor to condense to water, it's important to remember that a quantity of heat is going to be removed from the air, and this is called the latent heat. This is the reverse process of, say, boiling water. So if you think about your kettle at home, you've got liquid water in the kettle, you add a lot of energy, and then you cause it to evaporate and form gas. Here we're talking about the reverse situation where we have gas and we form a liquid, so we release energy. Okay, so the latent heat of condensation is the release of energy, and that's exactly equal to the latent heat of evaporation, which is the absorption of energy. Okay, and that latent heat of evaporation is the amount of heat that's added to turn water into vapor at the same temperature. There are two important equations for latent heat. The first relates to the latent heat of evaporation and condensation, and it's simply 597.3 minus 0.57 times the temperature, where the temperature is given in degrees Celsius, and it represents the amount of energy that needs to be used, for example, to evaporate or boil liquid water, or to condense vapor into liquid water again, okay, depending on whether you're using LE or negative LC. And you can see another interesting thing here, which is that as you get closer to 100 degrees, you get lower energy requirement, which makes sense. Okay, the second is just a single number, although we'll see a modification of this equation later on in another topic of the course. And what it says is that we need 79.7 calories of energy per gram of water to melt or freeze water. So obviously, if we're melting water, we need to add energy, and if we're freezing water, we need to take energy out. And note that 1 calorie here is 4.18 joules. There's another interesting realization here, which is that it takes about 7.5 times the amount of energy to evaporate a gram of water that it takes to melt a gram of ice. Okay, that brings us to the end of video 1 of topic 2.